Good evening. Today I'll first show you how we can use Simulink. So it will be a continuation of last week's discussion on the low pass filter. I just want to simulate it, the low pass filter using Simulink, and then show the step response, how to get that. So that will give you some idea about how to use Simulink. After that, straight away I'll jump across to feedback control and discuss some things about pole zero cancellation, winding up with a little bit of Simulink simulations, which will give you enough basics to take up task 2 in the project. So I will now switch to Matlab and Simulink first, show you how Simulink is used, and then continue.
Let me start from the scratch. First, we will start Matlab. Here it is. So it takes time, but yeah, here it comes. What you do usually is when the main Matlab program appears on the screen, right here, let's just wait, it is still starting up. On the command window, if you type Simulink and return, it's a bit slow, but it will happen soon. Yeah, there it is. So then a separate window appears. This is from where you can drag and drop different blocks. Now, the whole idea of Simulink is to build up control systems, complicated control systems using block diagrams, blocks. So you do it in a separate figure window or a worksheet. So you can open one of those worksheets by clicking this. So this is going to be my workspace to build up the control system. And then inside these different libraries, you find all sorts of different blocks that you can use. As an example, inside continuous block, I have this transfer function block. So what I'm going to do now is just click on it, drag and drop. So it appears on your command window. And then you can configure this one to represent whatever the transfer function you like. Now what I'm going to do is, let me just first open the M file that we have been dealing with last time, which is this one, I think. Yeah. And then let me find out my Simulink block diagram. So in this case, my numerator is 1 upon R into C. So if I double click, you have separate places to define what is your numerator and the denominator. So inside this vector, what you do is you define your numerator polynomial as coefficients. So your S term will be 0, and then it will be 1 upon RC, but R and C values will not be transferred to the Simulink block. Therefore, I'll type in the numerical value of R, which is 1 and 4 zeros, that is 10K, into I think it was 1 nanofarad or something, 0.1 5 zeros and 1. So that is the numerator polynomial. And then I'll do an easy thing. If I just copy and paste 1 upon RC as the second coefficient, or the coefficient of the constant term, to the denominator polynomial, I have now typed in this value into the transfer function. Now what? Now if I apply and close it, there you can see those values have been assigned to the transfer function. So now we can use this block to find out what is the step response. How to do that? We have to apply a step as its input. This is the input from where the signal is given to the block, and the output comes from here. So all what we need now is some way of giving the input to the system, and then some way of looking at the output. So if we go back to Simulink, in the sources library, you'll find, if you go down, you'll find the standard step signal. So you just drag and drop it and double click to configure it. Step time, I would like to have the step time not after 1 second, but just as we start. So when time is equal to 0, a step of 1 will be applied now, right? Say OK, and then you just click here, drag your mouse and drop it here. It will connect it. So this means that this step input coming out from the step block is now driving the input of the the RC low pass filter. Now what? Now in the sinks library, you can find out different blocks which are absorbing signals. Now in this case, best is to use the scope block, drag and drop it, connect it, and that's it. And then let me just resize it, and I'll save this as let us go into my working library. Here it is, and perhaps, yeah, why not, inside Matlab. Then I will say RC low pass, right? Save. Then in the simulation submenu, hang on, we can change the configuration parameters from the pull down menu. So it simulates for 10 seconds. 10 seconds I guess is too many. Let us simulate it for perhaps 1 second and see whether it reaches the steady state. So then all what you do is, if you click this one, it will execute the simulation for 1 second. It's done. Now if you double click on the scope block, there you are. See the step response. So even 1 second is too many. So let's simulate for 0.1 second for simplicity. I'll just close this one. Simulation configuration parameters, put it as 0.1 seconds, apply, OK, save it, simulate again, double click on the figure window, there you are. So now you can see a nice step response which reaches 1, and then 63% rise time is somewhere here. If you look down, it is 0.01 or 0.01 seconds, which agrees with what we have been discussing in the last workshop. So I'll stop the Simulink thing right now. You will get more and more exposure to Simulink and different blocks as we take up the pole zero cancellation thing. So this is a quick refreshment of how to get the step response for the RC low pass filter that we have been discussing last time. So in your task 1, you are supposed to simulate RC high pass filter, and then just think a little bit about how to do that. And now I'll jump across to pole zero cancellation technique and how to simulate that in Simulink. Let us start with the PowerPoint slides. I have named it as Simulink and controller design using pole zero cancellation. What are poles and zeros of a transfer function? Just consider the general transfer function where the denominator has n number of factors, s plus a1, s plus a2 up to s plus an, and the numerator has s plus b1, s plus b2 up to s plus bm, m number of first order factors. And then when you can see that when s is equal to b1, b2 up to bm, the transfer function gp s will become 0. Therefore, those values are called zeros of transfer function. And then when s is equal to a1, a2 up to an, you can see that the transfer function will become infinity, the value become infinity. Those values are called poles of a transfer function. And then what is feedback control? If there is an open loop plant or a process, let's say we got a power amplifier and a DC motor in combination can be the open loop process, and then we are after the speed of the DC motor shaft. So that is our output, and the process input then is the input signal to the power amplifier. Then if you want to introduce a feedback control system around this open loop process, what we do is we measure the output. If it is a motor speed, then typically we use a tacho generator or an incremental encoder to measure the output speed. Take it back, compare it with the set speed, reference speed that we want the motor to operate. And if there is a discrepancy, the error will be fed into a controller that we design. The controller will decide what should be the next input to the power amplifier. It will send that signal out to the power amplifier, and that closes the loop. Then it's called a closed loop control system or a feedback control system, with the idea that the output is measured and fed back to the beginning of the system. What is highlighted in red is the open loop system. What is highlighted in blue is the part designed by the control engineer in the process of introducing feedback control. And then quickly, what is PID control? Now, PID control is one form of controller that you can introduce. There are various types of controllers, but PID is, I guess, is the most widely used one in industry, the one which is easy to understand, and also the one which is easy to implement and also easy to tune, perhaps. What we do is we compare the reference and the measurement, take the error, and it is fed into 3 different blocks. First one is the proportional part, where the error is simply multiplied by a certain factor and sent out. Second one is the integral part, where the error is integrated, multiplied by a certain factor and sent out. Third part is the derivative part, where the error is differentiated, multiplied by a certain factor and sent out. The addition of all 3 components is the complete control signal which is sent into the input of the open loop process. Mathematical expression of PID in time domain, you can write it as the control signal output ut is equal to kp times et plus ki times the integral of et dt plus kd times det by dt, the derivative. And in S domain or in Laplace domain, if you Laplace transform these 3 terms, you get capital US is equal to kp times capital ES plus ki times over S times capital ES plus kds times capital ES. Taking ES out, I get kp plus ki over S plus kds, which is the transfer function of the PID controller. special cases of PID control. There can be PI control without the derivative part, then the transfer function will be Kp plus Ki over S. There can be PD control, proportional derivative control, without the integral part, then the transfer function is Kp plus Kds. But remember, there is nothing called ID control or the integral derivative control. Why? Now, if you think of the three parts of the PID controller, the proportional part always reacts to the present value of the error, whereas the integral part, you know that integrator keeps on accumulating the previous values of the error term, so it acts based on the past behavior of the error. That's the integral part. And the derivative part, you know that derivative is the tangent drawn to the error variation at the given instant. So the derivative tells you what is going to be the future trend of the error signal. Therefore, derivative part reacts to the future trend of the error. So when you look at that, it is obvious that there cannot be a controller which does not act to the present value of the error. Therefore, ID control is not possible. But as we said before, there can be situations where we are not bothered too much about the future trend of the signal when we take the control decision. Then you have PI control. And there can be other situations where we are not bothered too much about what happened in the past in the error signal. Then you can pick PD control. That is how you decide. And then what are the objectives of feedback control? Quickly, some of the important ones. One is, it could be to speed up the system response. Let's say your open loop system has this type of a response with a large time constant. Then you can introduce feedback control to speed up the process with a smaller time constant. If you think of the 0 to 63% rise time that we have been discussing. So this is the open loop step response in blue, and then closed loop step response in red, which is faster obviously. So time constant is improved, or the process is made faster by introducing feedback control. And then another objective would be to eliminate steady state error. This is your step input. Your open loop step response can undergo a certain transient period and reach a certain value, but which is not the input value at steady state. So then the error between the two, input and the output, is called the steady state error. And then sometimes there can be situations where we need to eliminate this steady state error. Then the preferred closed loop output, when you introduce the closed loop control, will exactly reach the final steady state value of the input. That could be one objective of feedback control. And disturbance rejection. Now if you think of the motor example, if you just try to break the motor shaft by applying some force on the motor shaft, if the system is open loop, the speed will drop. Perhaps it will pick up again a bit, but will not be the final value which was set before. But if you introduce feedback, it is possible to have the speed controlled in such a way that when there is a disturbance, of course there can be a slight dip in the speed, but it will pick up. Controller will hold the speed finally back at the previous set value. So those are some of the objectives of feedback control. And then how the system response relates with the location of the closed loop poles. System response depends on the location of closed loop poles of the open loop process. If you just consider this process K over S plus A, if you just follow the Laplace transform and the analysis that we did before to get the unit step response, final time domain expression will be like this: K over A times ut minus K over A e to the power minus at times ut. If you get this sketch, the input will be like this, just one line parallel to going through one parallel to the time axis, and then the output will be like this, and the final steady state value of the output will be K over A. And as you can see now, since the time constant is 1 upon a in this system, and a is the location, is the value of the pole in this transfunction. If you look at the complex S plane, this is where the pole is located at S is equal to minus a. And then, as you can imagine, if a changes, the time constant will change. That means this process will become faster or slower. So that is the relationship between the location of the system pole and the system response, or the speed of the system. And then now we have enough background to move into pole zero cancellation. A controller usually relocates the closed loop system poles such that the output response improves. So that is, from another point of view, that is the objective of the, or the task of the controller, if you look at it from a more mathematical point of view. And then in pole zero cancellation technique, what we do is we try to cancel this lower process pole using a zero introduced by the controller trans function. So that is what we are doing in pole zero cancellation. So now what I am going to show you is how to design a PI controller using pole zero cancellation technique for a simple first order trans function like k over s plus a. And now, if it is a PI controller, we know that the trans function of the controller is kp plus ki over s. When you take it to a common denominator, I can write it as s times kp plus ki divided by s. And taking kp out, I can write kp times, within brackets, s plus ki over kp divided by s. And then this is going to be the controller 0 that we are going to use to cancel the slower pole of the open loop trans function. Now if you look at the complete closed loop system, we got the open loop trans function here, and then we got the PI controller trans function here, and this is the feedback that we introduce. This is our input, this is our output in S domain as a block diagram. And then if you think of the signal flow direction, signal flows from left to right. Because of that, this path is called the forward path of the trans function. This is called the feedback path of the control system, not the trans function but the control system. Sorry. And then if I consider the forward path trans function, the total trans function, which is the product between this trans function and this one, you can see that I get kp times s plus ki over kp into k divided by s times s plus a. And then if you look at the controller 0 and the slower pole of the trans function, open loop trans function, then you can see the possibility of choosing ki over kp such that we cancel out s plus a slower pole in this forward path trans function. This can very well be done because ki and kp values must be designed or determined by the control engineer. So he has the freedom to decide what is ki and what is kp. So what we simply do here is we choose ki over kp ratio to be equal to a, which gives us one relationship in the process of finding out what are the values of ki and kp corresponding to this particular control problem. And if you now consider the pole 0 cancelled system, what is left in the forward path trans function after pole 0 cancellation is only these three. Kp times k divided by s is in the forward path trans function. And then you can reduce this feedback block diagram in such a way that you get a single trans function. What is that? You will have to do a bit of research on how to simplify this. I'll give you some links towards the end, and then it is up to you to do a bit of search and find out how to do that. And the final closed loop trans function will be kpk divided by S plus Kp K. We end up again with the first order transfer function. Then all we need to do is to think about what is going to be the another design criteria related to this. Now, a typical design criteria will be to achieve a certain time constant, a specified time constant. Say, reduce the open loop time constant by 50%. Now we know that the time constant of the closed loop system is 1 over kpk. And then the time constant of the open loop system, we know that it is 1 over a. So if we had reduced 1 over a by 50%, I can equate 1 over kpk to 1 over 2a, which is my second relationship. Then what? Then I can, from equation 2, I can easily find out what is kp, which is equal to 2a over k. Since the open loop transfer function is defined, we should be knowing the value of a, value of k numerically, which gives me what is the value of kp. And then from 2, I can find out ki, which is kp times a. Once kp is known, from 2, I can find out ki as 2a squared divided by k. And then I would like to take up a numerical example. Let us take our open loop process GPS to be equal to 5 over s plus 8. And then equation 1 will give me ki over kp as equal to 8. Equation 2 will give me 1 upon kp times 5, which is k, is equal to 1 over 2 times 8, which is 8. And that gives me kp is equal to 3.2, ki is equal to 25.6. And now what I am going to do is quickly construct this complete system in Simulink, and I'll show you what will be the output response of the open loop system for a unit step, what is going to be the output response for a step input in the closed loop system, and then we can compare how the closed loop system response is going to be much improved compared to the open loop process. Okay, let us start again. Now I have opened up Matlab and Simulink. There is a new window on which I will drag and drop a transfer function block first. I'll be a little quick here, but you can I'll be uploading this to Moodle, the Simulink block model. You can run it on your own. So as you can see now, the transfer function we considered was 5 divided by s plus 8. So let me just set the numerator and the denominator polynomials accordingly. That's done. Apply. Okay. So we got 5 divided by s plus 8. Then let me take the step input and connect it. So that's the open loop system. We are driving it from a step signal of unit amplitude, unit step. From these things, let us take a scope, hook it up, and then I will save this as in my directory. Here, Matlab. Let me call it 40 cancellation. Whole zero, yeah, whole zero cancellation. Saved, and then just to be on the safe side, I'll set up the sorry, Matlab path also. My computer data D CQ graduate teaching T term 1 2012 Matlab. Done. And now we go to this. Then, as I did before, we can just simulate it and see. So I don't think we need to simulate it for more than, let's say, 1 second. So I could change the time here also. Plus, I would like to do another thing. That is, I would like to plot the step input also on the same figure window. To do that, inside signal routing, you can find out the multiplexer block. So instead of sending in one signal to be plotted, you could also do this. You can take the reference signal out, take it here, connect it. So now I am plotting two signals on the oscilloscope, and the first one will be in yellow, the second one will be in purple, etc. So now I save it, run it again, and oh sorry, this is a small practical issue. How to set it? You go here, data history, you need more points here. Apply, okay, yep. And then let me run it again, save and run. What are we doing here? It's 0.7. I still can't see the step input. Okay. That I guess is, let me just zoom this a little bit and see. It should come right here. So I'll do one little trick just to see if that is appearing. Let us apply the step after 0.1 seconds and see what happens. So what we are observing is, I guess it's a simple plotting problem. Yeah, there it is. So now you can see at 0.1 seconds the step is applied and the output starts rising. But as you can see now, the input is 1, output is, it settles down somewhere around 0.6 plus something, right? So this is the steady state error in the system. So now I'm going to construct the closed loop system in parallel to this open loop system so that we can compare the two systems. To do that, let me just copy and paste the same trans function, and then the output, I would like to see that output also on the same plot window. So what I do is I increase the input ports of the multiplexer block, right? Keep it like this, connect the output of the closed loop system. We still haven't constructed the closed loop system. Let me do it little by little. And then from the math operations block, you can get a summing point. I will need two summing points. So if you right click on a certain block, drag and drop, you can get a carbon copy of the same. And then controller will have two components, therefore I need a summing point at that point, and then I need another summing point where I compare the reference and the measurement. And then input to the reference can be the same step. Then all I need to do is to introduce the feedback, which goes like this to this summing point, and then now I have to construct the PI controller. How do we do that? From the continuous block, no, before that, from the math operations block, I'll get this gain block, which can be my KP. So if you double click on the name of the block, you can type anything into that. A new name can be given. So this is my KP. And what is the value of KP? It's 3.2. If you double click on it, you can go into the configuration block, apply the value 3.2, and in fact you can see the value of KP also. Then you could simply connect the error signal into that. So the proportional path is now complete. Now we need the integral. So what you do is you get another gain block, drag and drop. This is your integral gain Ki, and you also take from the continuous block, you take the integrator, connect the two together. So instead of integrator, you also can rename it as S. That's not important. Let's not do that. I'll go back. Let it be integrator. And your Ki value is how much? It's 25.6. 25.6. Apply, close. Then you feed the error to that, like this. Yep. Sorry. Okay. Something like this. So now what? Now if you look carefully, we apply the same input, step input to the open loop system, take the output, plot it. We directly plot the step input, and we also feed the same input to this closed loop system where I've got the comparison between the reference and the measured output, take the error, feed it to the proportional controller, take the output, feed it to the integral controller, take the output, add the two together, feed it into the input of the system. So now if everything is correct, we should get the right plots expected. Let's hope we are lucky. Yeah. So now you can see that this is your input step, this is your open loop system output, and if you work out roughly 63% of 0.6, it will be 0.36 something, so somewhere here. Now since everything is working, let me just do one thing. I'll close this one and I'll reset the step so that we are applying the step at t is equal to 0, which makes it easier for me to calculate all the times, time constants, etc. like this. So now you can see that roughly my time constant is about let's say 0.8 or something, and then I'll need a time constant of 0.4, and then now the output of the closed loop system goes exactly to 1, which is the input steady state value of the input, which is good because there is no steady state error. And then the 63% is somewhere here, and if you go down, you can see that roughly we have reached the design criteria. So this is how you can implement a closed loop control system. One thing is how you can implement a closed loop control system in Simulink and how to simulate that together with the open loop response as well as the reference input, and also how you can design a PI controller using pole zero cancellation technique to meet the given time constant criteria. Now it is time for you to think about task 2, because I just completed a pole zero cancellation design for a simple first order system uh, and how to design a PI controller. But in your case, in the task 2, the open loop trans function is 10 divided by s times s plus 2, and you are supposed to design a PD controller, of which the trans function is kp plus kds, which can be rewritten as kd times s plus kp over kd. So all you need to do is to identify the slower pole of the process and the controller 0 that you will use in order to cancel that slower pole in the plant trans function or the open loop trans function. So I'm not going to tell anything more than that. On the task 2, you have been exposed to everything that is needed. So it is a matter of applying those concepts to this particular problem. And then these are some of the links. This PowerPoint slide will be uploaded in Moodle, so you can just click on these links to get more information. Those are some wiki sites links in Wikipedia. And in the library, if you find out Control Systems Engineering by Nice, this is the standard control systems textbook that we are using in our analysis of control, design analysis of control systems. That is the standard control course that the electrical engineering students follow. So most of the concepts that we discuss, not the pole zero cancellation design perhaps, but everything about the trans function, poles, zeros, system stability, etc. All those basic concepts are very nicely explained, including PID control. So just have a look at that one if you want to get more information. Yeah, I think that should be it for this week, and I hope you will enjoy the week 4 activities. Thank you. See you next week.